Myself Dr. P. Vijayakumar, Associate Professor, Department of EC, Aditya University. In today's session, we will be seeing the definition of cross power spectral density, and we will be solving the problems related to cross power spectral density using the properties of cross power spectral density. We will be computing the different parameters like a cross correlation function, cross power spectral density, cross power by solving the problems. Okay, at the end of this particular session, we will be learning two learning outcomes. One learning outcome is we will apply the cross power spectral density concepts, and also we will apply the properties of cross power spectral density in solving the problems. Okay, so let us recall the definition of cross power spectral density. Cross power spectral density is mathematically equal to Fourier transform of cross correlation function, or cross correlation function is the inverse Fourier transform of cross power spectral density. Both relations will be useful in solving the problems. And one more important definition of cross power spectral density is cross power spectral density is mathematically defined as Sxy of omega is equal to limit t tends to infinity expectation of xt of omega yt star of omega by 2t, or xt star of omega yt of omega by 2t. Both are valid. And one more important formula which we will be using for computing the average cross power. Average cross power is mathematically equal to cross correlation function at tau is equal to 0, or area under cross power spectral density with respect to frequency. Bandwidth multiplied by cross power spectral density gives me the average cross power. And the properties of cross power spectral density: even function, odd function, when their orthogonality is equal to 0, when they are uncorrelated with constant means it is equal to 2 pi x bar y bar of delta of omega. And the last property is very important, which is Wiener-Kinczi relation, and it is also a definition of cross power spectral density which we will be using very frequently in solving the problems. So let us solve few problems related to cross power spectral density. Let us see the first one. So the cross correlation function is given to us. Rxy of tau is equal to 4 into u of tau e power minus alpha t. Now we need to compute the cross power spectral density. What is the formula of cross power spectral density? Cross power spectral density is the Fourier transform of cross correlation function. So what is the formula? Minus infinity to infinity Rxy of tau e power minus j omega tau d tau. So substituting for u of tau e power minus alpha tau e power minus j omega tau, this is e power a into e power b, which is equal to e power a plus b. So 4, we know that unit step function is defined only for positive values. So u of tau is equal to 1 for tau greater than or equal to 0, and is equal to 0 for tau less than 0. So 4 into 0 to infinity e power minus alpha plus j omega tau, and the integration of e power minus at is e power minus at by minus a, and substituting that and substituting the limits, e power minus infinity is 0, e power 0 is 1. So what is the answer we got? 4 by alpha plus j omega, and the Fourier transform of 4 into u of tau e power minus alpha t is equal to 4 by alpha plus j omega. So this is a very simple problem. Next we will see one more problem. Now cross correlation function is given to us. Now we need to compute the cross power spectral density. So now we need to apply the inverse Fourier transform formula. Inverse Fourier transform. We know that the cross correlation function, time average cross correlation function, is equal to inverse Fourier transform of Sxy of omega. Now we need to compute Sxy of omega. So first they have given the cross correlation function. First we are computing the time average cross correlation function. So the time average cross correlation function is mathematically defined as limit t tends to infinity 1 by 2t minus t to t Rxy of t comma t plus tau dt. So limit t tends to infinity 1 by 2t. So substitute in the given function and doing the time average. So ab by 2 sin omega naught tau, and the time average of limit 2 omega t plus omega t. So what we will get? Sin t minus of sine of minus t. We know that the sine is a odd function. So, what we will get, sin t we will get 0, sin of minus t we will get. So, the residue which is available function is AB by 2 sin omega naught tau. This is nothing but the time average autocorrelation cross correlation function. Now, we know the relationship between cross power spectral density and time average cross correlation function. So, cross power spectral density is Fourier transform of time average cross correlation function. Applying that, what we will get, the Fourier transform of sin omega naught tau. So, we know that the Fourier transform of sin omega naught tau can be written as 2 pi into delta of omega minus omega naught minus delta of omega plus omega naught divided by j. So, simply substituting that AB by 2 into 1 by 2j, 2 pi by j, 2 pi by j. Here 2 cancels out. This can be written as sin omega minus omega naught minus delta of omega minus omega naught delta of omega plus omega naught by j. So, the solution is AB into pi by j. So, this 1 by j can be written as minus j. So, 1 by j can be written as minus j. So, this is written as AB into pi by 2 into minus j delta of omega minus omega naught minus delta of omega plus omega naught. Okay. Let us see one more problem related to the cross power spectral density. Two random processes are defined here. X of t is one random process, y of t is another random process. Y of t is the delayed version of x of t. So, y of t is given as delayed version of x of t. It is delayed by a delay of t seconds. Now, we are asked to compute the autocorrelation function of y of t, auto power spectral density of y of t, cross power spectral density, cross correlation function, cross power spectral density. Now, we will compute the autocorrelation function of y of t. Ry of tau is expectation of y of t into y of t plus tau. But what is y of t? X of t minus tau. What is y of t plus tau? X of t minus tau plus tau. X of t minus t plus tau. This is numerically equal to Rx of t2 minus t1. Next, since it is a Whitson stationary random process, t2 minus t1 is mathematically equal to tau. So, Ryy of tau is mathematically equal to Rx of tau. Next, Syy of omega is the Fourier transform of Ryy of tau. So, that is nothing but Fourier transform of Rx of tau is nothing but Sx of omega. So, Syy of omega is equal to Sx of omega, Ryy of tau is equal to Rx of tau. Now, Ryx cross correlation function, expectation of y of t into x of t plus tau, expectation of x of t minus tau, x of t plus tau. Now, this can be written as Rx of t tau plus t, Rx of tau plus t. So, cross correlation function is nothing but Rx of tau plus t. Now, using the time shifting property of Fourier transform, cross power spectral density is equal to e power j omega tau into Sxx of omega. So, we computed all the 4 parameters. Autocorrelation function of y of t, auto power spectral density of y of t, cross correlation function and cross power spectral density. Okay. So, these properties of power spectral density will be helpful in computing all the parameters. Okay. And one more problem we will see. X of t and y of t are two different random processes and they are related by the relation y of t is equal to x of t cos omega naught tau and omega naught is given as constant, and x of t is a stationary random process with a power spectral density is equal to Sxx of omega, and we are asked to compute the power spectrum of y of t. So, before that we will find the autocorrelation function of y of t. What is the formula of autocorrelation function? Expectation of y of t into y of t plus tau. But what is y of t? x of t cos omega naught t, and what is y of t plus tau? X of t plus tau cos omega naught t plus tau. So, taking x of t and x of t plus 2 in one side and applying the expectation, which is mathematically equal to Rx x of tau, and cos omega naught t and cos omega naught t plus tau is written besides to Rx x of tau. So, this is the autocorrelation function of y of t. Now, we will compute the time average autocorrelation function of y of t, so that we can apply the Wiener-Kinchy relation in the final step. So, the time average autocorrelation function is given as limit t tends to infinity 1 by t 2t minus t to t r by y of t comma t plus tau. So, Rx x of tau cos omega naught t plus tau. So, this is in the form of cos A cos B. Cos A cos B written as cos A minus B plus cos A plus B divided by 2. Cos A cos B is written as cos A cos B written as cos A minus B cos A plus B divided by 2. Now, the integration of this function will be 1 by 2 Rx x of tau cos omega naught tau. The integration of this function will be 0 because cos t minus of cos t, cos t minus of cos of minus t. We know that cos is an even function. Cos t minus cos t, what we will get? 0. So, this part will vanish. The residue portion or the residue term is 1 by 2 Rx x of tau cos omega naught tau. Now, for this one, we need to compute the Fourier transform so that we can compute the power spectral density. So, the power spectral density is the Fourier transform of correlation function. The Fourier transform of correlation function, this Rx x of tau cos omega naught tau, we know that cos omega naught tau, this based on the modulation property. There is a property in Fourier transform, modulation property. Based on the modulation property, a function multiplied with cos omega naught tau can be written as, Fourier transform can be written as x of omega minus omega naught plus x of omega plus omega naught divided by 2. Applying that relation, 1 by 2 into sxx of omega minus omega naught plus sxx of omega plus omega naught by 2 into 1 by 2. So, the final answer is 1 by 4 sxx of omega minus omega naught plus sxx of omega plus omega naught. Okay. Let us solve one more problem. The cross power spectral density is given to us Sxy of omega. You need to compute cross correlation. Very direct problem. You need to apply the inverse Fourier transform. Applying the inverse Fourier transform, and omega is limited over the range minus 1 to 1, a e power j omega tau. E power integration of e power at is e power at by a. Using that relation, this can be written like this. And here jb omega into e power j omega tau. Here we need to apply integral u dv rule, uv minus integral v du. Applying that rule and the expanding, substituting the limits, finally we will get 1 by pi tau square a tau sin tau minus b sin tau plus b tau cos tau. This is the cross correlation function. So, in this session what we have seen is, we have seen the mathematical definition of cross power spectral density, and also we have recalled the properties of cross power spectral density, and we applied the concept of cross power spectral density and the properties of cross power spectral density in solving the problems, and we computed many parameters like cross correlation function, autocorrelation function, cross power spectral density, auto power spectral density, and also average power. So, in the next session we will be starting the applications of random variables and stochastic process, which is nothing but noise. So, we will see what is meant by noise, what are different types of noises we encounter in a practical scenario, and we will classify different types of noise and how to estimate the amount of noise present in a signal, and how can we predict the average value and how to compute the average value of the noise. All those things we will see in the next coming sessions. Okay, thank you.